Hello, this is going to be chapter 4, some of that from the Solomon's book. So in this one we're going to be talking about alkanes, alkenes, alkynes, as well as how to name them mostly, as well as talking about cyclic structures. The simplest of the organic molecules are called alkanes, right? So they only contain carbon-carbon bonds and carbon-hydrogen bonds. The single bonds. The overall formula is that for every one carbon, you're going to have 2n plus 2 hydrogens. So it's going to be what's called completely saturated, only single bonds. These are almost exclusively derived from petroleum. So you can first get off from distillation. And the point at which it actually distills, those different fractions are used for different things. Very small things are typically used for like natural gas. Medium boiling things from anywhere from room temperature up to about 100 degrees are used for solvents. Above that, you're talking about gasolines and different kerosenes, diesel oil, things like that, fuel oil, stuff like that. And then you can also have the non-volatile liquids and non-volatile solids, and those are used for different purposes, anywhere from mineral oil, lubrication, up to paraffins and asphalt and whatnot. To get the alkenes and alkynes, they're typically broken down. Those components are further broken down by cracking, stuff like that. So they're heated up to very high temperatures, usually in the presence of a catalyst, to make the alkenes. So the shapes of alkanes, sometimes we'll talk about normal ones, and that just means that all the carbons are in a single line. So there's propane, butane, pentane, they're all straight, because you can also get branched alkanes. So where you don't have all of them in a row, but it's still you have some portion of them hanging off of what we consider to be the main chain, so the longest chain. So here you've got the 4 carbons here, and then you have a branch, just like a branch off of a tree. So if this is the trunk, that's the branch. So, as we learned in previous chapters, right, the more compact the molecule is, the lower boiling point. So the farther it's stretched out, so something like this. So this is hexane here, and so it's got a fairly high boiling point. But as you come down, they all have six carbons. When you get down to here, it has a much lower boiling point. So how do we name these things? Well, one of the problems is that a lot of natural products have common names. A lot of structures have common names. So here it's vanilla. It's one of the components of vanilla. Geraniol is from geraniums. Azulene is from these mushrooms. They're these blue mushrooms, and then morphine from the opium poppies here. The problem comes with what happens to the naming of these things if they're in a different language, or even within the different regions of a country. They may have slightly different names, and it's just going to be a little unwieldy trying to figure out all those names. Lots of times they still use the common names, stuff like that, but what we really need is something that's more systematic, and that's where the IUPAC comes in. IUPAC is the International Union of Pure and Applied Chemistry. So they are the ones that set the rules. So they are the governing body of the names. So they're mainly located, I believe, in New York City and in Switzerland. But their actual mailing address for administrative stuff is actually just down the road from my university, in the Research Triangle Park in North Carolina, so in Durham. So naming of alkanes. Okay, so again, they're the simplest carbons. It's all sp3 hybrid. All the carbons are sp3. You'll hear them called saturated, and also sometimes you hear them called aliphatic, which is the Greek for fat, because they are going to be those typically going to be made up of the solid fats that you come across. Okay, so you're going to need to know this. You're going to need to know this chart. I usually typically just up to 12 carbons long, but know that methane, ethane, propane, butane. Those 4 are a little bit weird, and we'll talk about that in a second. From 5 to 12, it's actually just a more traditional naming, right? Pent, for prefixes, pent for 5, hex for 6, hep 7, and on for it. methane, so that comes from the Greek for wood, so because this is typically done, this methanol, so which is the single carbon alcohol, it was derived from wood, so it was distilled off from wood. I don't know about ethane off the top of my head. So propane, so the first indication was from propionic acid, so 1 and 2 carbon acids are completely soluble in water, but the 3 carbon one had some limits to solubility, and so pro, meaning first, they're using that because it's the first fat. So that was the first one that didn't completely be solubilized. Butane, again, this was the first encountered this in butanoic acid, and stuff like that, which is what you can get from rancid butter. That's where they derived it from, and so it's from the Greek for butter. But then after that, it becomes more normal. Stuff like that, and so these branches that go away we also call them side chains, stuff like that. And so you'll have this main chain, which is the longest continuous chain of carbon atoms, stuff like that. So, and then you'll have the small things hanging off of it. And so sometimes the main chain doesn't have to be the horizontal. Here it is, but here we can make, so for here be 1, 2, 3, 4, but I can find a longest chain that's 1, 2, 3, 4, 5. So this would be the longest chain. And then you'd have the 1 carbon branch here. So be careful. Okay, the side chains, so if you have more than one, stuff like that, and so what you're going to need to know is if you have 2 of them, 2 of the same side chain. So if you have 2 chlorines, it would be it'd be dichloro. So if you have 3 of them, it'd be trichloro, tetrachloro, pentachloro, and so on and so forth. You are going to need to know those prefixes. Those are going to be important. Okay, so for naming the alkanes, okay, so I tried to be standardized about this, or to be systematic about how you go about this. So you're going to see this 4-step approach over and over again, repeatedly. And so, because what I wanted to show is to say you're going to use the same sort of steps to go through there, but there's going to be small differences between the naming of the different classes of compounds, and it's really those differences that you need to know. Okay, so the first thing we mentioned about get the main chain, stuff like that. So it's the longest carbon chain. Now, you cannot go back up, stuff like that. So you need to be able to like take your finger and go like this and go from one end to the other. You can't like come up here and then go back and go back down a bond and then keep going. It needs to be a continuous chain. Okay, so with that, so anything. So you name that, and then you come back to that group, the methane, the methane, ethane, propane, whatever. So with that, so that's going to be the name of your longest chain. So we've got those carbon atoms covered. Okay, now we need to deal with the atoms that are hanging off of it. So with that, and so for here, what you're going to want to do is say, figure out those side chains, those branches. Now the thing is, with the side chain, the atom is either part of the side chain or it's part of the main chain. It can't be both. Okay, so with that, so once you've named those side chains, you'll see me usually circle it because that means we've named those atoms, and it's the side chains that now those atoms that need to be labeled. But we can't just say that a side chain is a just use that methane. Ethane, because it would get confused because you'd have ethane, methane, or whatever it is. Methane, ethane. Kind of hard to do. So with that, so to denote a side chain, what we do is we take off the suffix, the ane suffix from those names, and add yl. And so ethane becomes ethyl, propane becomes propyl, butane becomes butyl. So with that, so any side chain, you can denote that by putting a yl as a suffix instead. Okay, so then the next thing we have to determine the detachment point, where that side chain, what carbon of the main chain is that side chain hanging off of. But the thing is, we need to figure out the side that has the smallest numbers. And so what I'll do is, what you see me do is I'll write a list, stuff like that. And so we're going to go from one end to the other and do that naming, and then we're going to go back the other way, stuff like that. And we'll keep track of where those things are. What you do is just add them up, and whichever has the lower sum, those are the numbers that you use. Okay, so with that, and so here, the next thing you do is you put the alkene in alphabetical order. Okay, so so ethyl will become before methyl, which will come before propyl. Okay, it doesn't matter anything like that. So you put the attachment numbers in front of the alkane group, so it'd be like 2 ethyl, 5 methyl, something like that. So and whenever you're going between a letter and a number, or a number and a letter, either way, usually use a dash. Okay, so for that, so if you have more than one type, so if you have 2 methyl groups, say, you're going to need to list both of those numbers out front of the methyl. Okay, usually separated by a comma, and usually we do them in increasing order. So it would be like 2, 3 dash dimethyl. So with that, we have to indicate that we have 2 methyls. So with that, so you have to put the di out in front. Like that. So the now, if I have a di, like a dimethyl on here, I have to have 2 numbers, even if they're the same number, because we want to make it unambiguous. If it's if you write 2 dimethyl, I'm going to ask you where the heck is the other. We can't assume that the other one's on 2. Okay, so you would have to write 2 dimethyl. So again, if it's the same, it doesn't matter if it's the same number. Write it. If I have a di on the side chain, I need 2 numbers. If it's a tri, I need 3 numbers. If there's tetra, I need 4 numbers. Okay. Now, one thing I mentioned, I probably should have moved that up there. The non-number prefixes, things like cyclo, iso, things like that. We'll talk about that in a minute. Those do not count. Those do count on the alphabetical, but the di, tri, whatever does not. Okay, so if you write it in, if you were to write it on that list, okay, you make those. That's what you're alphabetizing. Okay, don't worry about the di and the tri and whatever. All right, so be careful. So after you've listed that out, the parent name comes, that very first name that you came up with, the very first step, that goes at the end, no matter what. Don't put that alphabetical in front or whatever. No, it always goes at the end. Okay, so it'd be like methyl, ethyl, octane, or whatever it is. 2 methyl, 3 ethyl, octane, stuff like that. So 2 methyl, 3 propyl, octane. Right. So even though you would think that the octane should come before the propyl, nope. The main chain always comes at the end, no matter what. Okay, so here we go. So with that, so we're going to name this compound. Now this is where the dots can help when you're learning this. Okay, so we've got dot, 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 dot. Like this. Okay, so that's what we're going to do. We're going to come in here and find the longest chain. Okay, now usually we start at the horizontal. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, but we're also going to want to go down the side chain. So 1, 2, 3, 4, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. Right, but remember the way that the naming is set up. It's so that no matter how you draw the molecule, it'll still have the same name. So let's start from this side, right? 1, 2, 3, 4, 5, 6, 7, 8, right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. So in fact, this is the longest chain right here. Okay, so it's C9. Okay, and that ends up being nonane. Okay, that's gonna be the name. So we've named those 9 carbons. Okay, so the side chains are gonna be this one, and this one. Okay, so a 1 carbon chain, or 1 carbon side chain. That would be methane, but we're gonna name it methyl. Okay, same with this one. Right, so the meth indicates 1 carbon. The YL indicates it as a side chain. So here we have a 2 carbon piece. Right, so it would be ethyl, right? Eth would be 2 carbons, YL side chain. Okay, so what we're going to do is we're going to say, okay, we're going to assume this is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so that means if we're going to use this numbers, right? So this methyl's hanging off of 3, this one is hanging off of 5, and this ethyl's at 6. Okay. The other way you could do it is to say, okay, well, what if this is number 1? Because we don't know. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so here the ethyl is hanging off of 4. This methyl, well, again, is off of 5, and this one is off of 7. So if you add these up, okay, so with that, so this 9, this is 14. If you add this up, that's 12, that's 16. So we're going to use these numbers here because notice how they added up to a lower number. Okay, so with that, so here, next up, right, we're going to alphabetize these. So ethyl comes before the methyl. Right, so with that, and so it's going to be, we're going to list this as 6 ethyl. Okay. Now we have 2 of them, so it's going to need to be dimethyl. But we'll put the numbers out front, so 3, 5. Okay. Notice how to put a dash anytime there's a number between a number and a letter. Right? I usually dash between numbers. It's usually a comma. Okay. So with that, so we've dealt with all these, and then no name at the end. Okay, some people like putting a space here. Some people don't. Stuff like that. So I like putting a space because it's a little bit easier to see. Okay, so with that. So, but for me, I don't care. So with that. So if you want to double check, okay. So with that. So when you were, if you were to give this, if you have the name to indicate the structure, it's usually better to go backwards. Okay, so with that, start with the main chain. So this says we have a main chain that's 9 long, right? So right here. Okay, so we have 2 methyl groups, one hanging out at carbon 3, one hanging out at carbon 5. Okay, we also have an ethyl group, 2 carbon side chain, right? It's hanging out at carbon 6. So right here. Now, one thing I didn't point out, and this is a common mistake, is to say, like, this is an ethyl group because you go into the main chain. No, no, no. These 9 carbons here are taken up with the no name. We've already named those. It's the ones that are away from the side chain that we name, right? So this is a 1 carbon piece because this carbon here has already been named in the side chain. Same thing here. This carbon has already been named, so we only need to name these 2 atoms here. Okay. So for here, so we do lots of what is it? Lots of examples here. Okay, so put in your dots when you're starting out. Okay. So here we go. Right. So 1, 2, 3, 4, 5, 6. 1, 2, 3. 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. Okay. So we have a 7 carbon main chain. Right. So C7. So if you look at your chart, right, it'll be a heptane. Okay, so now here, right, we've got 1, 2, 3, 4 methyl groups, right? So go ahead and list them, all of them, right? 1 methyl, 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 methyl. Okay, so if we're going to start from this side, we're going to be 1, 2, 3, 4, 5, 6, 7. Okay, so it's going to be 2, 3, 4, 5. So if we start from this side, right, it'd be 1, 2, 3, 4, 5, 6, 7. Right, so here it'd be 3, 4, 5, 6. Okay, so we're going to add them up. Right, so it's what, 5, 10, this is 14. Okay, this is 18. Okay, so these are the numbers we're going to use. Okay, so it ends up being, right, so the methyl out here, so it becomes tetramethyl. Right, 2, 3, 4, 5. Right, I got a tetra, I need 4 numbers out here. And then the main chain at the end, so heptane. Right, so there you go. Try to save some paper here. The right. Okay. So with that, so for here, right, so 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, right? So it doesn't really matter, stuff like that. And it turns out for here, we it would all end up being the same. Okay, so one thing I forgot to mention on here. Let's go back. Is that if there's an issue, we're picking the main chain. If you have 2 ways to determine it, or two ways that you can get the main chain. What you're going to want to do is you're going to want to have more smaller side chains than one big one, right? So it's better to have, you know, 3 methyls than it would be to have a big, you know, T-butyl group, or, you know, big butyl group, stuff like that. And so you want to have more smaller ones. So if I take this horizontal one, right, I have 1, 2, 3 methyls. If I take, say, this one here, again, it'd be 1, 2, 3 methyls, right? So it's going to end up being the same, stuff like that. So traditionally, I usually use the horizontal, just because I think it's a little easier to see, but it would not matter, right? If you started here and used those as the side chain, that's totally fine. Stuff like that. So 1, 2, 3, 4, 5, 6, 7, 8. Stuff like that. So C8, right? So that's octane. Okay. Stuff like that. And so here we go. So we have methyl. Pen's running out. Stuff like that. So I'm mostly using methyls just for simplicity's sake, but it ends up working out the same. Stuff like that. So here we go. So we have, right? So with that, so if we're going to start on this side, right? It's 1, 2, 3, 4, 5, 6, 7, 8. Okay, so it ends up being 2, 6, 7. Okay, but for this side, right? So we're going to do 1, 2, 3, 4, 5, 6, 7, 8. Right? So with that, so it ends up being 2, 3, 7. Okay. So you add them up. So this is what, 13, 15. This is 12, right? So now this one ended up being the top one. Okay, so we put this together, right? So it's trimethyl, right? Ends up being 2, 3, 7. Okay, octane. There we go. So there's our name. Oops. Okay, so for this one, I'm going to draw this. There's actually a carbon here at that intersection point. I'm going to draw them a little bit sloped, so it's a little bit easier, bent, so it's a little easier to see. Okay, so here we go. So start with the horizontal, right? 1, 2, 3, 4, 5, 6, 7. Right. We go down side chains. 1, 2, 3, 4, 5. Right. Now we need to start on this side. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Stuff like that. So here's the problem, right? This is when this comes up. This sort of obscure rule. Okay, so if we took these carbons here as the main chain, we would have this group here, which is a single, could be considered to be a T-butyl group. Okay, which we'll talk about those in a second, but it's one big group. If in fact we take this one where it goes down, we have a methyl-methyl-ethyl. Okay, and the rule is you want more smaller side chains as opposed to one big one, and so the main chain is going to be these carbons here. 1, 2, 3, 4, 5, 6, 7. So C7, right? So it's going to be heptane. Now the side chains, right? It's going to be here and here, right? So for that, and notice how these, yes, those methyl groups are hanging off the same carbon, but they are independent side chains. Okay, so we have an ethyl, methyl, methyl. They just so happen to be hanging off the same carbon, right? So if we go 1, 2, 3, 4, 5, 6, 7. Okay, the methyls are both hanging off of 2, and the ethyls at 3. The other way that we could do it, right? 1, 2, 3, 4, 5, 6, 7. Okay, so the methyls are hanging off at 6, and the ethyls at 5. So we're going to add them up. Right, so this is 7, 12. This is 17. Right, so we're going to take these numbers here. Right, for here, ethyl comes before methyl. Right, so for that, so it ends up being 3 ethyl, 2 dimethyl, heptane. Now notice that yes, the di is here, but we don't count those like the dis, the tris, and that sort of stuff. You just look at what's listed here. Ethyl comes before the methyls, right? So it gets listed first. So 3 ethyl, 2 dimethyl, heptane. Okay. Okay, so some branched chains. Okay, so for that, and so for this one, the so what happens if it's not connected to the main chain? So if you have say a main chain here, okay, and you have a 3 carbon piece here, okay, so 3 carbons, right? So this is propyl. Okay, let's say you have another main chain, okay, but let's say it's connected like this. Okay, so it's still a 3 carbon chain, right? So this 1, 2, 3, right? So this would be 1, 2, 3, right? So it's still a propyl, but it's connecting to the main chain through 2. And so this one, I like to call it a 2-propyl group. That's, I think, the technical name for it. Stuff like that. But you can also call it an isopropyl group. Now, in here, when you're doing the naming, the prop, and if you use this case, it would be the propyl that you'd have to alphabetize. For here, the iso counts, and so here the iso would end up being the what you would use to alphabetize. And so the question is always, well, what if it's listed like this? Right? It's still 3 chains, right? So that's 3 propyl. Actually, what we do is we reorder the numbering, right? 1, 2, 3, and so this just becomes a regular propyl group again. Okay, so what's happened is you can get free rotation around this bond. What's happened is that bond's just gone like that, and so it's just a regular propyl group. So this is called a 2-propyl group or an isopropyl group. You can use either one. About that. So just be aware. For butyl, okay. So with that, so again, you have the main chain. So if you're going to have 1, 2, 3, 4, right? So this is a usual typical butyl group. Okay? So isobutyl has branch right here. So you move this guy over to what you've done is you move this one over to here. But since it's still 4 carbons, it's called isobutyl. Usually don't not a big one on this one. Secbutyl is similar to 2-butyl. Okay, it's a secondary carbon because it has 2 carbons. It's the second one. It's a secondary off the chain. So secbutyl, I would call it a 2-butyl group. So for that. So the last one being T-butyl. Now I usually do use T-butyl. It's right. So it's got 1, 2, 3, 4. That's why it's considered a butyl. But this carbon here, if you discount the main chain, it's tertiary, so it has 3 carbons to it. So this one is almost always tert-butyl. It's technically tertiary butyl, but lots of times you'll just see it abbreviated as T-butyl. This is one where I actually will write it as T-butyl. It's technically it's 2-methyl-2-propyl, stuff like that, but T-butyl is usually a little bit easier to indicate. Oh, one thing I forgot to mention with the isopropyl, okay, and this actually comes up. Question students ask this quite a bit. So this is T-butyl, okay. That not T-butyl, isopropyl or 2-propyl, okay. Well, here, let's do this. Okay. So here's the main chain, right? So if we do the same thing, but write it like this, okay, this is not an isopropyl, okay, because here's the main chain, okay, we've already named this carbon here, so for that, and so this is just 2-methyl, so this would be a dimethyl, okay. Here, the connector into this main into the main chain is away, right? So for here, you're connecting these 3 carbons for here. Here, what's happening is this carbon here is named as part of the main chain, so it's not going to be part of the side chain. So here we just have 2 CH3 groups that are separate and independent. So be careful. Some students mess this up. Okay, so as far as classifying atoms, so this is we usually indicate this as what kind of carbon is it hanging off of. The reason why with the only exception, again, this was on the previous chapter. Nitrogen is one of those that we can actually have secondary, tertiary, secondary, or primary, secondary, tertiary, whatever. Everything else is always what is the carbon hanging off of it, stuff like that. So for here, if we want to say, if we're looking at, we're interested in this hydrogen here, so with that, we look at, well, what kind of carbon is it hanging off of? And here, this carbon has only one carbon attached, so it's primary. So this is a primary hydrogen, primary. This hydrogen here is dependent on the carbon that it's hanging off of, right? So this carbon has two, so secondary. This is tertiary. So this is tertiary hydrogen. Everything is dependent on what kind of carbon it's hanging off of, except for nitrogen. Nitrogen, we do that separately because it can have 1, 2, 3, 4 different things hanging off of it. So oxygen's usually, like an alcohol, it's usually going to be just an OH and that's it. Chlorine, whatever, stuff like that, it's just going to have the one bond. But nitrogen is a little screwy. So speaking of chlorine, so naming haloalkanes, stuff like that, and so what we do is, again, indicate that it's a side chain. Instead of the YL, we're actually going to lop off the I and E and just add O. So fluorine becomes fluoro, chlorine becomes chloro, bromine, bromo, iodine, iodo, stuff like that. So we treat halides just like any other side chain. There's no priority to it. We just treat it just like like if it was any other sort of like a methyl group, stuff like that. So stuff like that. And so if we have this haloalkane here, stuff like that. So 2, 4, right. Here, fluorine, right? So put in your dots. Okay, so for that, so the main chain, right? So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 1, 2, 3, 4, 5. Right? 1, 2, 4, 5. Right? 1, 2, 3, 4, 5, 6, 7, 8. Now, as it turns out, it wouldn't actually matter which of these 8s that you picked, right? Because if we picked the horizontal 8, we'd have a methyl isopropyl fluorine. If we went down here and say like that was the main chain, we would have a methyl, an isopropyl, and a fluorine. Right? So since the groups are the same, it actually doesn't matter. So I'm just going to pick the main chain, or the horizontal chain, just for simplicity. So like that. So it's C8. Right? So it ends up being octane. Now the side chains are this methyl. Okay. This 2-propyl group. Right? It's a propyl because it's 1, 2, 3. But it's connecting to the main chain through carbon 2, and then the fluorine here, right? So that becomes fluoro. Okay, so if we start at this end, right? There's 1, 2, 3, 4, 5, 6, 7, 8. Okay, so it's 2, 3, 6, something like that. So if we go from this side, it'd be 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this ends up being the methyl hanging off at 7, this is at 6, this is at 3. Okay, so this is 11, this is 16, so we're going to pick these numbers here. Now, since we since we use the 2-propyl, we go fluorine, propyl, methyl, right? So for that, to do the alphabetical, so fluorine's going to be first, so it's going to be 6-fluoro. After that, it's the methyl, right? So it becomes 2-methyl. The propyl is next, so it's 3, and this is where I like parentheses, 2-propyl, because you just kind of bolt that in. Okay, octane. Now, if instead you used isopropyl here, okay, now it would be methyl isopropyl fluoro, and so now the name would be, right, fluoro would still come first. Okay, so with that, so it becomes 6-fluoro, but now you put the 3 isopropyl in, and then the methyl comes last. It'd be 2-methyl, methyl, octane. Okay, so you can do it either way, but you have to be careful about this. Now, for naming an alcohol, okay, so with that, so for this one, to indicate this an alcohol, you're going to use this OL suffix. Okay, so for that, and so, but the parent chain needs to be the longest stretch of carbons that has the alcohol in it. So even if you can find a longer carbon chain, a longer carbon main chain, if it doesn't have the alcohol in it, we can't use it. So it's the longest one that has the alcohol in it. Now you name the side chains, or find and name those side chains, and then we're going to do those do the numbering. Now, two things. One, the alcohol gets the priority. Okay, so if we end up putting the suffix out here, stuff like that whatever the suffix is here, that's what gets the priority. Stuff like that. So we want to be at that end, stuff like that. So that the end closest to that is gonna be C1. Okay, so in here we're putting the OL at the end of the main chain, so the C1 is gonna be the side closest to that. And so we go 1, 2, 3 from there, stuff like that. But we are going to need to know where that alcohol is. Okay, is it a 2? Is it a 2 alcohol, or is it hanging off a carbon 3 or a 4? So what you'll see me do in the list is I'll just write like alcohol in there, just to, but I'll put it in quotes so that I remember. Oh, I don't put that in there. That's what the OL is for. Okay, so with that, and then you put things in order as needed, okay, as normal. Okay, so here we go. So OH, right? So you put in your dots. Okay, so if you're looking at the main chain, right? So with that, so it goes 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, 6. Oh, so this is going to be the main chain. So C6, right? So normally be hexane, but since we have the alcohol in here, we're going to take that off and then add OL, so hexanol. Okay, so with that, and so the main, right, so the side chain, right, so we're going to have this methyl group, but also the alcohol. Notice I put that in quotes because we're not going to incorporate that into the name, but we need to figure out what that number is. Now this alcohol, right, it's closest to this side, so it ends up being 1, 2, 3, 4, 5, 6. Okay, so it doesn't matter about the adding them up on this one. This is the side that's closest, so we're going to use that. So the methyl's at 4, the alcohol's at 3. Okay, so we're going to put this out front. So 4-methyl, 3-hexanol. So this is actually the older way of doing it. The other way that you could do it, this is the newer method, is you actually put, say, 4-methyl, hexan 3-ol. Okay, what the idea being is that you put the name right next to what it is that you are, the number right next to what it is that you're indicating, stuff like that. So I usually do, if this is how I learned it. This has been kicking around for 15 years or so, stuff like that. And so you often see this one. So I'll take either one. Most chemists will take either one. It's just whatever you prefer. Okay. Now, if you have more than one of these groups, okay, so you have 2 alcohol groups. So how do you handle that? Well, you do it the exact same way, but you have to indicate you have 2. So now at the end, we'll put this as a diol. Okay. So with that, and so here we go. So OH, like that. Put this in. Put your dots in. Okay. So you don't forget that there's a carbon here. Right, so like that, and so the main chain is either going to be 1, 2, 3, 4, or 1, 2, 3, 4. Right, so we'll do the horizontal. Right, so it's 4 carbons. Right, so usually that would be butane, or butane. So like that, but it's going to be, take this off. It'd be butanol. But we have 2 of them, so it becomes butan diol. Okay, because we have 2 ols. Right, so 2 OLs, we have 2 alcohols, right? So with that, so the side chain here is a methyl, right? So and then we have those 2, right? So with that, so alcohol, okay. And so this is the side closest to an alcohol, right? So it's 1, 2, 3, 4. So this one's at 1 and 2. The methyl's hanging off at 3. So the way we would name it would be 3-methyl. 1, 2 butanediol, or you can name it 3-methyl butan 1,2 diol. Okay, so I'll take either one. Doesn't really matter. Okay, so for naming a cycloalkanes, okay, so this is where we are. Right, so we have these rings. You hear me? Even something like a triangle or a square, those end up. I'm going to call those rings because the main chain is going to cycle out back onto itself. Okay, so for that, and so to indicate that, right, we're going to put a cyclo out front. Okay, so to name these things, first thing we need to do is we need to figure out which is longer. Is it going to be the ring, or is it going to be any of the side chains that are hanging off of it? Now, when you're naming these things, you're either part of the side chain, or you're either part of the straight chain, or you're part of the ring. You cannot be part of both. Okay, so you can't like go straight chain and then go into the ring. That's not going to fly. So for that, so you're just going to you need to take just the ring, count those, or just the straight chain. So with that, so if the ring, if the straight chain is longer, then you name it like any other side chain, and then the ring becomes a side chain. So for that, so and you know like any other side chain. So if it was a cyclo butane group that was a side chain, it becomes cyclobutyl. If it was a cyclohexane, so that was the main chain, it would become cyclohexyl. Right. So you take off the N, put the YL on there to indicate that it's a side chain. Okay. So with that, so the but again, you're going to need to know that indicate that it's a cyclic structure. So the main chain is going to, if it's the ring that's the main chain, you're going to need to put that cyclo in front of the main chain. Okay, so with that, name the side points. Now, the problem is going to be so getting the lowest number. Okay, because since it's a ring, where is carbon 1? Okay, and so what you're going to want to do is you're going to take a look at the different contact points, and so or the different side chains, and say, okay, so this side chain is let's say this is 1, and then let's say this side chain over here is, well, let's say this is 1, and then there's one over here. You say, okay, well, what if that's 1? And then you go and you do the number sets. Now what you're going to want to do is you're going to want to go, you can go clockwise or counterclockwise, it does not matter, but what I tell you is that you're going to want to go either clockwise or counterclockwise towards this nearest side chain neighbor. And so if here and here, right, so you can 1, 2, whatever. So then you're going to go 3, 4, 5 around. Okay, if it happens to be over here, right? So with that, so you would say 1, 2, 3, right? And then 3, 4, 5, and then just keep going around. Okay, so with that, so you're going to want to give everybody an opportunity to be number 1, and you add them up, and use that side chain. Now, if there is a tie of the lowest number set, okay, and there's no other way to resolve it, okay, it's like baseball. So with that, so if there's a tie, they had to determine what the heck is who wins. So they in baseball they said the runner wins, right? Because the ball has to beat the runner. So with that, and so so with that, for here they had to make a choice just like that. And so what they did is they said, okay, we are going to the first alphabetically is the one that gets the 1. So with that, and so that gets the higher priority. Okay, so and then you put it together just as normal. Okay, so we've got this one. So this first one. Okay. Okay, so put in your dots. Okay, so for here, right, you have a 6-membered ring here, right? 1, 2, 3, 4, 5, 6. Okay, but you have a 1 carbon main straight chain, a 2 carbon straight chain, and a 1 carbon straight chain. None of those is larger than 6, and so the main chain is going to be here. Okay, so this is C6, which would normally be hexane, right? But it's a ring, so it's cyclo hexane. Okay, so with that, so the main chains, right? So the side chains, right, are here, here, and here. Okay, so you have methyl, ethyl, methyl. Okay, and so we're going to say, okay, so let's say this is 1. So we're going to say 1, 2, 3, 4, right? So 5, 6. The reason why I did that, I said, okay, let's say this is 1. The nearest side chain, if you were to go clockwise or counterclockwise, the first time the closest this one's going to be closer. So we're going to want to go. In this case, we're going to go clockwise, right? So like that. So because if we go here, boom, we've hit a side chain. If we go here, we have to go all the way around to hit this one. So we go. So this is the closest one. So then we're going to just keep going around. Okay. So for so it ends up being right 1, 2, 4. Okay. Now for this one, if we said okay, let's say the ethyl is 1. Okay. Now here it takes 2 carbons to meet our first side chain. Here it only takes 1 carbon. So this is going to be 2. So now we're going to go counterclockwise. So 1, 2, and then keep going. 3, 4, 5, 6. Right. So now it's 2, 1, 5. Okay. Now for the last one, we can put this one as 1. And so if we go this way, it's only 2. We meet our first neighbor. Here it's 3. Or yeah. So 1, 2, 3. All right, so with that, and so for here, we're going to want to go again counterclockwise. So 1, 2, 3, 4, 5, 6. Right, so ends up being 1, 3, 4. Right, and notice how everybody had an opportunity to be number 1. And so with that, so we add these up. So this would be 7. This would be 8. This is also 8. So this is going to be the numbering we want. Okay, so we compare methyl and ethyl, right? So ethyl's going to win, so it becomes alphabetically. So 2 ethyl, right? 1, 4 dimethyl, cyclohexane. So there's our name. Okay, so for this one. Okay. Okay, so for this one, we have a 5-membered ring, right? 1, 2, 3, 4, 5. Okay, for here we've got 1, 2, 3, 4, 5, 6. Or we could do 1, 2, 3, 4, 5, 6. Right, but either way, the main chain is going to be longer. Or the straight chain is going to be longer than here. Now you cannot go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No, that's not going to that's not going to fly. Right? You're either part of a straight chain or you're part of a ring. You can't be both. Okay. Now the question becomes: do we take this 8, or that 8? Well, if we take this 8, okay, we're going to have this one large 6-carbon group. If instead we take the horizontal, this one. Okay, we're going to have a methyl and a cyclopentyl. So remember, we want to have more smaller chains. So we have a 1-carbon side chain and a 5-carbon side chain. We're going to want more smaller ones. And so our main chain is going to be just this. Okay, so 1, 2, 3, 4, 5, 6. So C6. So it'd be hexane. And so our side chains are going to be this one and this one. So here, right? So it's 5 around. So it's pentyl, but since it's a ring, we need to indicate that, so it becomes cyclopentyl. Okay, it's 5. The side chain is 5. The pent. It's a side chain, so it's YL, so it's pentyl. But those are in a ring like this, and so it becomes cyclopentyl. And then we have the methyl. Okay, so we need to do from both sides, right? So 1, 2, 3, 4, 5, 6. So this ends up being 1. Oop, this is 1, 2. So if we do it the other way, just 1, 2, 3, 4, 5, 6. Remember, because for alkanes we need to go both ways. So like that. So this becomes 6 and 5. All right. So this 3 versus 11. So we're going to take those numbers there. So cyclopentyl, right? Because we've listed it here. So cyclopentyl comes before methyl. So it becomes 1 cyclopentyl, 2 methyl hexane. There we go. Hey, we got them right. Okay, so for this one, right, so struggling with the class, right? So this, if you put ears here and a little, right, so with that, so you know, a little dog, right? So it kind of looks like a little dog, doesn't it? Right, kind of looks like a little. So with that, so anyway, stuff like that. So for here, right, the you end up with right. So the ring is 4 around. Okay, here the tail is right, it's 1 carbon long, and the head is 2 carbons long. Right, so the main chain is going to be the body here. So with that, so it becomes C4. Right. So normally that'd be butane, but what we're doing here is right. So indicate the ring is cyclobutane. Okay, so the side chains, right? So the tail here is 1 carbon, so it's methyl. The head here, right? So it's ethyl. Okay, now we need to do the numbering. So we're going to say, okay, let's say that's 1. So going clockwise gets us to a side chain first, right? So 1, 2, 3, 4. Right? So it ends up being 1, 2. So if we give this guy, the ethyl, the opportunity to be lead dog, sorry, bad joke. Here, so the first time we get to a side chain is going counterclockwise, so it ends up being 1, 2, 3, 4 like this, so it ends up being 1, 2, right? So if you add them up, 3, 3, and we have a tie, and so and there's no other way to get rid of this. The smallest numbers, the smallest sums are both the ties, so we have to go to the rule book, and it turns out that the first alphabetically, in this case ethyl, gets the 1, so we end up having to use those numbers there. So it ends up being 1 ethyl, 2 methyl, cyclobutane. There you go. Okay, so alkenes. Okay, so with that, so here, this is where you've got a carbon-carbon double bond. We have it called unsaturation, stuff like that. And so for here, that's going to be given a priority, right? Because we put the suffix in, stuff like that. So we find the longest chain; it has to include that double bond. Okay, we find the side chains. We use those as normal. Now we are going to need to include the alkene in quotes, right? Because we are going to need to know that where the double bond starts with that, and so with that. So we need to find the attachment points, but the numbering, just like the alcohols, the chain starts at the side closest to the double bond, so for that, and then you put it as normal. You just as all the other ones. Okay, and so if we have this one. So it's here, here. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. Right. So here he is. So this one wouldn't even work, right? Even if it was longer, because it wouldn't have part of that double bond. So 1, 2, 3, 4, 5, 6, 7, 8. So C8. Normally that'd be octane, but since we have a double bond, it becomes octene. Okay. And so the side chain here, doing this in blue, we have an ethyl, but we need to know where that double bond starts, so we'll do the alkene. Okay, so this side ends up being the side closest to that double bond, to where that double bond starts, so it ends up being 1, 2, 3, 4, 5, 6, 7, 8. So the alkenes starts at 2, okay, and the ethyl's at 5. So the name ends up being 5-ethyl 2-octene. The other way you could write it would be 5-ethyl oct-2-ene. So you could do it either way. Okay. So for this one, right, so this is the end of a chain, right? So like that. So right, so you end up being right 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. So we're going to end up needing to be this one. Okay, so C7, right? So that's normally it's heptane, but since it's a double bond, right? So heptene. Okay. So for that, so we have this side chain here, so it's methyl, and we also have the alkene we needed to account for. So for that, so for the numbering, right? So this is the end, it's closest to the start of the alkene, right? Since it definitely starts there. 1, 2, 3, 4, 5, 6, 7. Right. So the alkene starts at 1, the methyl is at 5. Right. So for that, so when we put this together, it becomes 5 methyl, 1 heptene. Or the other way that you could do it is 5 methyl, hept, 1 ene. Take either one. Okay, so for cycloalkenes, okay, so now we're going to combine the two, but we do have the priority. So it's just like naming the regular alkanes, but now we've got a priority group with the double bond in there. And so what's going to happen is that that double bond, it's either going to be one, it's going to be one, those two carbons are going to be 1, 2. The problem is we don't know which one is 1 and which one's 2. That's where we have to do actually the lowest number set. But you know, it's one, you know, if you go 1, 2 and then keep going around the clockwise, and 1, 2 keep going counterclockwise, so you're going to have two numbers you need to add up. Okay, but otherwise it's the same as what we've done with the cycloalkane. Just applying this cycloalkene. So if we have this one here, like that, putting in the dots. Okay, so this that double bond is part of the ring, you know, part of the ring, and so that gets the priority. So no matter what, it's going to end up being the main chain. Right, so but that's, so this is the main chain, right? So for that, so we have C6, right? So normally that'd be hexane, right? But since it's a ring, it's cyclohex, hex, and we have a double bond in it, so hexene. Okay. With that, and so the side chains we have are ethyl, and then methyl. But we also have to indicate the alkene, where the alkene starts. Okay, so if we're going to say this is 1, okay, what we're going to want to do is going to say this one has to be 2. So 1, 2, 3, 4, 5. Right, so this would be 1. And the ethyl's at 6. The other way we could do it is say, okay, so let's say this is 1. It's 1, 2, 3, 4, 5, 6. With that, so this way the ethyl is 3, the methyl is 4, and again the alkene starts at 1. So what we're doing is saying we're going to go clockwise through the double bond, or counterclockwise through the double bond. Now one thing you can't do is you can't do 1 and then have this be 2. You have to assume that the 2 is the other end of the double bond. Okay, so when we add these up, so this is 12, this is 8. So we're going to use these numbers here. So for that, and so ethyl comes before methyl, so it becomes 3 ethyl, 4 methyl. Now you can put the 1 in. I would suggest doing that just because while you're starting out, you could get away with just having methyl cyclohexene, stuff like that. But it's good to go ahead and put that in while you're learning. Is a good habit. Right? The other way you could do it is 3 ethyl. 4 methyl, cyclohex 1 ene. Okay, and then there's no ambiguity. Nobody's going to care. So, okay. So naming alkynes, it's exactly the way it is naming alkenes. So with that, except now you're using the YNE suffix. So with that. So otherwise, it's just like naming any other alkene. Okay, so like that. So we've got this one. Now, I usually draw them as a sawtooth here for the double bonds, but remember for these, the bond is actually coming out. It actually looks like this, like that, because there's actually 180 degrees here and here. So for that, but I usually draw it like this, although put that triple bond poorly. So it's just for simplicity, so it's easier to see, so you know where those dots are, because there is a dot here and here as well. But as you're starting out, I usually use those as a, still incorporate the sawtooth. Okay, so here we go, right? So the 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, right? We can do 1, 2, 3, 4, 5, 6. Now, we couldn't do that even if it was longer, right? Because we have to incorporate that triple bond, so the main chain ends up being the horizontal, so 2, 4, 6, 7. So C7, right? So normally that'd be heptane. Since we have a triple bond, it becomes heptyne. Okay, so for here we have this 2-propyl group, right? It's 1, 2, 3, so it's a propyl, but it's connected to the main chain through carbon 2, so it's a 2-propyl. And then our triple bond starts, so alkyne. Our alkyne starts, we need to let the person know where that's starting, but we know that this is the priority group, so 1 is automatically going to be here. So 1, 2, 3, 4, 5, 6, 7. Okay, so alkyne starts at 2. The 2-propyl group's at 3. So when you put this together, it's going to be 3 2-propyl, 2 heptyne. But you could also list it, combining a bunch of things. You could also say 3 isopropyl, hept2-ine. Oops. Okay, there's a couple of different ways that you could do it. Oops. I hope you. Oh yeah, no, you can see it. Okay, so physical properties of alkanes. Okay, there's not a whole lot we can do with them, but we noticed this in the previous chapter when we were talking about melting and boiling points, is that the longer the chain, the higher the melting and boiling point, generally. So again, more compact structure, you're going to have lower boiling points. So you have this one here. You have octane here, and this is the this version of octane still has carbon-6, but the boiling point's lower because it's much more compact. You can also think about the main chain would be a lot shorter. Something like that. So, so now we're going to get into rotations. So for this, what we're going to be doing is taking a look at the fact that carbon-carbon single bonds can rotate and stuff like that. And so what we can do is we can have these what are called the conformers. They are different conformations. They're just temporary as we sort of rotate around. If you hold this this front carbon fixed, we sort of rotate the bundle. But we could also do it like this as well. So either way. Okay, so there's a couple of different ways we can do this. We can either do it through what's called a Newman projection, which is literally looking down the carbon. Oops, it's kind of hard to see. Okay. Okay, and so the circle is actually this front carbon. Well, you can't see the back carbon, right? Because it's being shielded by it's being hidden by the circle itself. But you can tell that there's things coming off of it, which are those little lines coming out the side. Okay, so you can't see the back one, but you can see what's coming off of it. It's kind of like your little brother sneaking up behind you in a picture, giving you bunny ears, right? You can't see him, but you can see the bunny ears. Okay. The other way that we could do it is indicate this with wedges and dashes, right? So for here, this is in a line, so this hydrogen would be, say, on a wedge. This one going away as a dash, stuff like that. So, okay. So, so to draw these things, okay, so we're going to set this here and try to aim it towards the camera, okay. What we're going to do is we're going to say, okay, you look down this carbon-carbon bond here, okay. Okay, and so what we're looking at is what are called the dihedral angles, which are the angles between a carbon in the front, a group in the front and group in the back. Okay, so for here, this is 60 degrees, and so if we're going to, this is 60 degrees here. This is 180 degrees. That's the dihedral angle. Okay. Okay, so if it's in this form here, where you have these 180 degrees. Okay, this is called the staggered configuration. Okay, if in fact you rotate this around, and so the front and the back, there's no difference, right? So they're right on top of each other. This is what's called eclipse, just like a solar eclipse, right? The sun and the moon get in the way of each other. So here. Now, what I also should point out that do I talk about that? We'll talk about anti in a second. So about that, and so if you were to plot these, okay, so there's a lot of steric repulsion going, and when you have an anti configuration, or excuse me, a eclipse configuration, the groups are actually able to feel each other. So here and here and here, okay, and stuff like that. And so that's gonna create a little bit of repulsion. And so what you do, so now this book doesn't list them, so I'm not going to do that. But what you would do is you would say, okay, that one's worth 4 kilojoules per mole. That's 4, and that's 4, and so you would just add them up. Okay, so when they're staggered, if they're hydrogens, they're so small in those staggered configurations, there's no energy penalty for repulsion. And so when it's in this configuration, it's staggered, in order to get over to here where it's rotated. Okay, so if you take this and you just rotate it like that, you're going to need to go through this eclipsed one and then fall down in the energy to get down to here to another staggered configuration. So this is sort of the barrier for rotation. Okay, and so if you look down let's say we take butane, so now we're looking at, let me see if I get these. Let's see if I can build one here quickly. So now we've got methyl groups that are hanging off of these guys. Okay, and so here we're still looking through carbon 2, carbon 3. Right? Put this back. It's a little hard to see. Okay, so here, like these are the two hydrogens. You have a methyl group coming off of here. You have a methyl group coming off of here. Hydrogen, hydrogen. So as you come around, right? So this is staggered, and this is actually a very special version of staggered. It's actually what's called anti. So the big groups are 180 degrees from each other. So this group here, but as you rotate around, so we're going to hold the back one fixed. So this is anti version of staggered. And then eclipsed, anti, eclipsed. But even when they're like this, okay, they are staggered. Okay, it's actually going to be okay, stuff like that. So it's going to be fairly stable, or there's not going to be a whole lot of steric strain. But the problem is these groups. Notice how the methyl groups are sort of hanging out towards each other. Well, those two methyl groups are actually feeling each other even when they're staggered. And so this is what's called a gauche interaction. It's a very small interaction, but it is important, stuff like that. So here, anything with gauche with a hydrogen, you're not going to feel it. But if it's anything other than a hydrogen at 60 degrees from each other, you're going to feel it. And this is the worst, okay, when the big groups are eclipsed with each other. Okay, so they're feeling each other right here. This version here. That is the worst. Okay, so when the big groups are together. So here we start here at the anti, and then rotate eclipsed. So you would just add up those 3 interactions if you want to get the energy. Here we have a gauche interaction. When you move them together, that's eclipsed. It's a really bad eclipse because you have 2 methyls. And then go back to a gauche, and then eclipsed, and then you go back to an anti, and then you can keep rotating around. Stuff like that. So this one here, just to highlight the gauche, the biggest groups are 180 degrees from each other. Okay, so if you were to add all these interactions up and plot them as you rotate around, you end up getting this sort of bumpy curve. Okay, and notice how the heights are a little bit different because for here this eclipsing interaction isn't nearly as, if you add those up, isn't going to be nearly as high as having the 2 methyl groups. Okay. Stuff like that. And so that's how you would plot these. Okay, so for cyclohexanes, so for cyclic structure, there was a big debate in the 1900s about how these things were configured and stuff like that. And so we thought, okay, well, if these are flat, there was a contingent of people who said, okay, well, when you put these together, they're flat, stuff like that. And so if you would do this, so if they were flat, what you would expect is that you would want these carbon-carbon bond angles to be as close to the normal 109 of a tetrahedron as possible. The farther you are out from the 109, the more less stable they are. So with that, and so here you're 49 degrees out from a cyclopropane. Here you're only 19 out. Cyclopentane, right? You're only out by 1. Okay, so if you go and you estimate that, cyclohexane, you're actually 11, but 11 the other way, and so like that. And so what you would see is you should see, if they were flat, a peak or a sort of the 5-membered ring of these 4 should be the most stable. And so what they did is they did lab measurements where you basically burn them, and the more energy it gives off, the less the less stable it is, and stuff like that. And so for here, 3, 4, yeah, that's what you would affect. But it turns out that this is more stable than that. Stuff like that. And the reason for that is the fact that they are in fact not flat. They are puckered a little bit. Stuff like that. And you also have these other strains. So you have an angle strain. That's, how far out of whack are you? On here you have torsional strain. Stuff like that. So as the bonds have to be twisted, and the steric strain, where these two things are whacking into each other, stuff like that. And so for here, if you look at this, what's happening if you do the Lewis structure of the cyclopropane, what's happening is you have 2 hydrogens that are eclipsed, and there's nothing you can do about it. Okay, with the cyclobutane, what's happening is they are still eclipsed, but not quite, because it can pucker itself, it can sort of twist, right? So with that, so it's like standing up for a while, right? You lift your one leg, that'll take the pressure off a little bit, and then you lift up your other. That's what's going on here. It's taking the pressure off of these hydrogens a little bit by twisting slightly. Same thing happens here. You can twist a little more, and so they're almost completely staggered, these hydrogens here, stuff like that. But once you get to the cyclohexane, they are completely staggered. Okay, so everything is staggered, and so you say, well, that's a Gauss interaction there, but if you draw this out, what's happening is from here and here, notice how they are pointed away from each other. These 2 hydrogens here and here, they're pointed away. Stuff like that. So these guys here. So they won't feel it. Stuff like that. And so they don't feel each other. So this one here in this configuration has none of those. Everything is staggered. Everything's happy. And this is what's called the chair structure. And it sort of goes like this, right? So there's a head on one side and then a feet on the other. Stuff like that. And so that's very happy. The cyclopentane does, the way that it does is we said it puckers, and actually if you basically takes a 5-member ring and sort of move one bond up a little bit, it creates what's called an envelope structure. So like you have the flat envelope, and you just take the little part here, move it up. That's what it looks like. Stuff like that. But the cyclopropane and cyclobutane cannot twist like that to be able to relieve it. Now you can get what's called pseudorotation or chair flips with this. So remember, with carbon-carbon bonds, you can get this you can get this free rotation around here. The problem is with the you can't quite do that with your cyclohexane, but they still wiggle around. Okay, and so what happens is these things will chair flips. So this is the original chair. Okay. And so what can happen is this can come up and this can come down, and now you're well, it's kind of hard to see here, but it's still in the chair form. But but now the feet and the head are flipped, and so you can go here and here, and so again the feet and the feet and the head have flipped. Okay, so every one of these carbons, right? So these are going to have 2 groups, and then one of them is going to be axial, one of them is going to be equatorial. Also, one of them is going to be up, one of them is going to be down, right? So like that. So this is down, this is up, down, whatnot. Now the axial. So with that, so if you notice, I'll draw it out here so it'll be easier to see. Oops. Okay, so if you have a group here, right? So let's say this is a chlorine. If you notice, the carbon-carbon bonds, right, are basically pointed up. So they always point towards the axial. Okay, so this is axial up. Okay, and so the ones down here, right? Notice how these are pointed down. That means that your axial. So in this case, say it's a hydrogen. This would be axial down. So So the axials all point up, so say like this is a globe, right? The axials go up and down. The equatorials go around the equator, right? So they're going to be coming off to the side. Okay, so here's a hydrogen, here say it's a chlorine, right? So this one here is equatorial down, okay, right? Because that's pointed up, that's down. That's higher than this, so that's up, down. Here, right? So this is higher than that, so this is up, right? But it's pointing off to the side, so it's equatorial. So so it's equatorial up. Okay, so axial does not necessarily mean up or down. You can have axial up, you can have axial down. Same with equatorial, you can have up and down. And so the thing to do is notice how they flop in between with that. And so, but every carbon is going to have an axial and equatorial. So it's easy to find the axial, okay, and the equatorial just kind of goes off to the side. Okay, so even for here, right? Notice how these bonds are kind of pointed down, right? So that means your axial is down, axial. Here the bonds are kind of pointed up, right? So that means the axial's up. And here the equatorial just kind of comes out to the side. But notice how this one is lower than that, so this is down. This one is higher than that, so this is up. The axial is higher than the equatorial, so it's up. Okay. The problem is you can also do chair flips. Okay, and so when that happens, if you take your model kit, what's happening is you move this side up and this side down. It goes to here. Now, what ends up happening is the axial and the equatorial flip spots. Okay, and so here, when you flip, right now the axial is pointed down, and this one down. So the thing that's down is axial. Here, notice how the carbon-carbon bonds are pointed up. So the this is up. And so now the bromine is axial. The ups and downs don't change. It's just, but all when the chair flips, equatorial becomes axial, axial becomes equatorial. Okay, so you can get some partial flips. Okay, and so this is here, so you get here, right? And so these actually knock together, and so it's not particularly stable, but it is a boat structure, and it's kind of like a paper boat, and so you can actually get these here. It's more stable than a half chair, but boats are never going to be more stable than the chair because you've got this interaction here. Okay, these guys here. So the easiest way to draw these chair structures, I've always found, is to start with the middle ones. Okay, is to just start like this. Okay, and then put on one side, put it high, and the other side put it low, and then just connect the dots. That's it. You got yourself your chair. Now, if you want to do a chair flip, okay, you would keep those four the same, okay, but you move that there. So now this was high, so over here at the chair flips it's low, and for here it's low, so now it's high, and so there's your chair flip. Not too bad. Okay, so now what happens if, we're not just dealing with cyclohexane in here, right? So what if we have things substitute? So when we say substitute, basically we've swapped something in for a hydrogen. There was a hydrogen there, let's put something else in there. Okay, so now these conformations are not going to be equivalent. Okay, so in this group, this methyl is axial, and this one is equatorial. The problem with that is in the axial, you get these flagpole interactions. Okay, and so here, right, so let's say this is the methyl group, you're going to be interacting with these guys here. Okay, these other hydrogens that are axial, and so even though they're far away, you can still feel them. Okay, and so even if we do like the chair flip here, so with that, even down here, this one down here is going to be interacting with these two axial hydrogens as well. Okay, so with that, and so what you want to be able to do is you want to be able to chair flip in order to be able to get the largest thing into the equatorial position. So you're going to want to chair flip it so that if it's axial, you want to chair flip it to turn it equatorial. Okay, and so you can sort of see this here, right? So just cyclohexane, it's going to be 50-50. No problem. But as soon as you put a methyl group on here, it spends 95% of its time in the equatorial position. As that group gets larger, it's going to spend less and less time for the axial because it's going to be hitting those flagpole hydrogens here, the axial hydrogens here and here, it's going to be spending more. And so once you get to a giant t-butyl group, now it spends 99.98% of its times here. So it's basically locked into whatever position that gets that t-butyl group equatorial. Okay, so with that, and so with di-substituted, okay, you could, if say the groups are pointed in the same direction, okay, that's going to be so it's either up, up, or down, down. That's going to, we consider that to be cis. If there's one up, one down, they're going to be trans. Okay, you can either look at it like this. So here, they're both wedges, so that we consider that to be both up, something like that. So that would be cis. If they were both dashes, they would also be cis. But here, if you have a dash and a wedge, or a wedge and a dash, you know, stuff like that, one up, one down, stuff like that, and so those would be trans. Okay, but don't get axial and equatorial mixed up with up and down, okay, or the cis and trans. Those are two separate things. Okay, and so what it's going to do is it's going to want to try to minimize this. Okay, and so this cis methyl group here, right, so with that, and so here you got the methyls. So if you go and plot it, right, so this one's going up, they're both going up because the axials are going down. And so it's going to spend all of its time in this one, because if they go into the axial, if you chair flip into here, it is both axial, or they're both axial, stuff like that. But if you have the trans version of this, where one up and one down, you're always going to have one equatorial, one axial, and there's no way that you can chair flip out of it. And so it's going to favor both of these equally, stuff like that. But for here, it's going to just favor that one. Okay, so for here, right, so with that, so you're going to say, okay, which molecule is more stable, right? So this is coming up, this is going down. So we have this right here. So we have the t-butyl group axial and the methyl group equatorial here, because notice the carbons are pointed up, so there's an axial hydrogen here going up. The other version we can have is this one here, where this is equatorial, right, because there's an axial hydrogen down, because the the two carbon-carbon bonds are pointed down. Look at that. So, and this one is axial. So like that. But for here, this one has, right, so we can't get them both equatorial. Yeah, that would be the ideal case, but one of them is axial, and so this one here is the one that has the fewer interactions. The largest group is equatorial, so that's where it's going to want to be. Okay, so for bicyclics, so with that, so here we've got two carbon rings fused together along, sort of along a bond. You can actually have them fused at one carbon, and that's called a spiro. Those are kind of cool. So by that, you can have cis and trans versions, right? So depending on where those two hydrogens are, if they're pointed in the same direction, it's cis, so this is cis-decalan, and this is trans, where you have an up and a down. Right? So with that, so if you have steroid structures, where you have a bunch of 6-membered rings and a 5-membered ring, they're going to usually be in this trans configuration. You can have multiple cyclics, so adamantane, and you get a whole bunch of 6-membered rings here, like that. So that's fine. So as far as reactions of alkanes, right, there's not a whole lot we can do with them. We can either burn them, either in race cars, or you can do it in candles, right? So with that, so we're burning the paraffin in there. So with that, so the other thing we can do is we can hydrogenate them. And so for here, what we can do is we can take hydrogen, molecular hydrogen, in the presence of some sort of metal catalyst. It's either going to be pure, or it's going to be on like a carbon support, and you take double and triple bonds and turn them into single bonds by adding hydrogens across there. Okay, so by that, so here we could take that double bond and make it into a single bond, double bond, single bond, triple bond, single bond. So it's pretty simple. Okay, and so for here, what we can do is we can actually calculate how much, sort of we can get some information about this. You're going to hear me call this degree of unsaturation. So with that, it's technically now the index of hydrogen deficiency, which is probably a better name, but it's I don't know, it's a little harder to say. So I usually just stick with degree of unsaturation. And so what we can do is if we look at a formula, we can tell how many rings plus pi bonds, right, double and triple bonds there are. So with that, so because each level of unsaturation leads to 2 fewer hydrogens. So if you look at fully saturated, so ethane versus ethene, right, we've knocked out two hydrogens. We have 2 fewer hydrogens over here. And so what we can do is we can say, okay, so C6H10, these are all different isomers of C6H10, but the degree of unsaturation is the same. So if you go and do the calculation, there's 2. So by that, so you can either have 2 pi bonds, so here and here. You can have a ring and a pi bond. 2 rings, right, or 2 pi, again, 2 pi bonds, but they could be on the same carbons, right? So 1, 2 pi bonds there. So we know how many rings and pi bonds, and so this is going to be important later on when we're talking about structures and stuff like that. And so you can go through this whole complicated calculation, but this is one of those where we use this formula: DOU equals 2C plus 2 plus N minus X minus H, all divided by 2. So this is one of those formulas that I'll give this to you on the test, but it's an easy one to remember. So it's 2 times the number of carbon plus 2, this is a constant, plus the number of nitrogens minus the total number of halogens. Now they don't have to all be the same, right? You can have like 3 fluorines and a bromine, right? That would put this as 3. So for that, and so minus hydrogens. Okay, and so we have this one. Right? So C6H10NBr. Okay, so the DOU would be equal to 2 times 6 plus 2, plus we have a nitrogen, 1, minus the number of halides, right? So we have one bromine, minus 10. So it's 12, 14, so 12, 15, right? Minus 11, 2, right? So 4 over 2, so it's 2. There's 2 degrees of unsaturation, okay? So by that, so down here, right, so C5H7NO2, right, so DOU, 2 times the number, right, 5 carbons plus 2, there's 1 nitrogen, no halides, minus 7 hydrogens. Notice I did not include the oxygens. The oxygen is not part of this equation, so don't put it in. Okay, so for that, so 10, 12, 13, so 13 minus 8, 2, so, oh, no. Oh, wait, excuse me, there's 0 of this, so this should be 7. Sorry about that. So for that, so I was thinking of this one. So right, so this is 6 over 2, 3. That's just more of what I was thinking. Okay, so it's 3 degrees of unsaturation, right? So we look at this and we say, okay, yeah, that makes sense. So this is an isomer of it, right? It has 1 bond or 1 ring and a pi bond. That's good, right? So for here we have 1 ring, that's 1 degrees of unsaturation, and 2 pi bonds, right? I never said they had to be carbon-carbon pi bonds. So these here, CO, this is CO pi bond here, CO pi bond here, so 1, 2, 3. So for that, so there's your 3. So this is one of the isomers, if you're interested. There you go. I know it's long, but good luck.